And a lot of what we do in this course is elective material, which means that I have the option as a teacher of the course to teach certain things and not teach other things. This is purely elective, but I will tell you that the likelihood of you having to know this for the exam is pretty high. Okay, when the exam comes closer and closer, I'll talk more about the expectations. The other elective topic that we might do tomorrow, I would never ask you directly about on an exam, but what we're going to learn tomorrow if we do it is there's a really slick way to find limits by using derivatives. It's called L'Hopital's rule. And the only reason why I want to potentially include it is every year I usually get a chance to talk to former students who are in post-secondary, and I ask them, what's something that we didn't do that you thought we should have done or could have been helpful when you took calculus in university? And they almost always say L'Hopital's rule. Anyway, that's not what we're doing today. Today we're looking at slant asymptotes. We're going to be determining equations of slant asymptotes and then graphing functions completely, including slant asymptotes if they exist. So warm-up 1. We're going to be talking about a function that's a sum of two other functions. And my grammar is a little tortured here. It says consider a function of the form f of x, that's the function, which is equal to g of x plus h of x, where the limit as x approaches infinity of g of x is 0, comma. The word exists. I don't know what I was trying to say there, but if the limit as x approaches infinity of g of x, which is only part of the function, is equal to 0, obviously it exists. But the limit as x approaches infinity of h of x does not exist. So what we're saying is that at very large values of x, g of x approaches 0, and h of x doesn't approach anything. Okay? By the way, your textbook teaches this in a very different way, and I've never been able to wrap my head around that way. So this is my take on slant asymptotes. Explain what this means about the behavior of the function f of x at large values of x. So what we are saying is that f of x is always going to be calculated, the y coordinate is always going to be calculated by taking the sum of these two. And if you've taken Math 30-1 already, and that's not everybody in the room, you will understand that this is a sum of two functions. And basically we can think of g of x as a function, we can think of h of x as a function, and we can think of f of x as being the function that's the sum of the two functions. But what we learn in Math 30-1 is that boils down to the y coordinate on f of x will be the sum of the y coordinates on the other two functions. Okay? So who can tell me what this means about the function or the behavior of f of x at large values of x? Given these two statements. Jack, you want to give it a crack?
Does y approach infinity?
Well, it may approach infinity, or it may approach negative infinity, but that's not the point. And let me explain what I believe you're thinking. And this is, you have to look at this in a unique way. I think what Jack is saying is, as x gets very large, g of x drops out of the equation. Right? Because if I were to say, what is g of x as x approaches infinity, it's 0. And then I think what Jack's saying is, since the limit as x approaches infinity of h of x does not exist, then that must be infinity or negative infinity. But there's another subtler thing about this. And it's kind of why I've said at large values of x. And I don't even want to get too close to infinity. Yeah.
Would the function f of x just not exist entirely? Because when you're adding the two functions, h of x doesn't exist, so then you can't add them at large values?
I like what you've said there, because what you've said is entirely true with one exception. What you've said is, the function f of x will only exist if both functions exist. And then what you've said, and here's the mistake, is you've said f of x, you've said g of x does not exist. G of x exists, it's just equal to 0.
No,
That
I meant h of x.
h of x is still going to exist. Whatever h of x is, just because the limit doesn't exist, doesn't mean we can't put a value in for x and find the y coordinate. It's just going to be really, really big or really, really small. By really, really small, I mean in the negative infinity direction. So these both exist. I mean, imagine, I can give you an example here, okay? We'll just jump ahead. If I look at this function, don't worry about what we're going to be doing with this. This is our g of x in my analogy, and this is our h of x. Just without using limits, looking only at the exponents on that rational part, which is called g of x, we should know that y equals 0 would be an asymptote of that function alone. So what that means is that as x approaches infinity, g of x will approach 0. Whatever 1/3 x plus 3 is, I can still put in really large numbers and it's defined, right? But all I'm saying is that big numbers, this, I mean, I don't want to give it away. At big numbers, that part is approaching 0. I think Sasha might have it.
Do they kind of like average out?
Can you elaborate on that?
Like if you've got your slope of nothing, and then say the slope of h of x is going up to infinity, does the slope of f of x just kind of go in the middle?
Okay, so first of all, by slope, I think you mean the graph, the y. And the answer is no. Because when you average 0 in something else, that's not mathematically a fair thing. When you're finding out the value of this, if one of these things is 0, you're not going to say the value is the average of them. I know kind of why you would think that. Any other ideas? I mean, I almost gave it away by saying that at large values of x, g of x doesn't matter.
Is f of x just h of x?
F of x is not h of x, but f of x will approach h of x.
Oh, okay.
Because, so let's write this down now. And I don't want to use limits here. I just want to say as x gets very large, g of x will approach nothing. And that means g of x plus h of x will approach h of x. Because g of x is dwindling away to nothing. But since g of x plus h of x is f of x, what we're saying is what Miles said, with a little tweak. I mean, I tweaked it to make it more precise. But if g of x is approaching 0 and f of x is the sum of g of x and h of x, then f of x is approaching h of x. It doesn't become h of x. It becomes really close to h of x. And the reason is this. The reason why it doesn't turn into h of x is because g of x never does become 0. It becomes really close to 0. So f of x is going to become really close to a small number plus h of x. Now, when you start talking about, say, a horizontal asymptote, we say that the function approaches that value of y. Here what we're saying is the function is going to approach another function. And we're going to see what that looks like in a minute. Write an expression for the limit of f of x. I mean, I do want you to understand, everybody, that this thing I'm asking us to evaluate is that. That's what I'm asking you to evaluate, because f of x is g of x plus h of x. Well, we know there's a property of limits. We don't often employ properties of limits, but it's true that the limit of a sum is the sum of the limits. So that means that this is equal to 0 plus whatever this limit is. Because g of x is equal to limit, the limit of g of x as x approaches infinity is 0. And here's where we have to be very subtle in thinking about this, because I think it was Jack who said, when I had asked, what's the behavior of f of x at very large values of x, I think Jack said, it doesn't exist. And the reasoning was because this limit we're left over with doesn't exist. But taken in a subtler fashion, what we're saying is, since this is the limit as x approaches infinity of f of x, and I've never thought about it this way, that's just struck me in the brain, what that means is that f of x becomes close to h of x, just by comparison, by looking at that. So what does this mean? Okay, let's take a look at what it means visually. I guess first of all, we're going to determine this limit. We're going to use a specific example here. What is this limit equal to? This is the limit as x approaches infinity of 2x over x squared over x squared over x squared plus x over x squared minus 2 over x squared. And you did this yesterday on your quiz, right?
We have a 2 in front of our x squared.
You have a 2 in front of your x squared? Okay, it's not going to matter. I just wanted to make sure before I committed to that. I don't know why I don't have a 2 here. Doesn't matter. So is that matching yours now? How many of you see it? It won't matter. Okay, but to be consistent, I have to put it there. So yesterday when you did your quiz, you would have done this to determine the horizontal asymptote of a function. Keep in mind what we are finding the limit as x approaches infinity of is not the entire function. It's only the first part of the function. So this works out to the limit as x approaches infinity. What do we get? 2 over x on the top. On the bottom we have 2 plus 1 over x minus 2 over x squared. This, and this will all approach 0 as x approaches infinity. So what we are left with is 0 over 2 plus 0 plus 0, which is 0 over 2, which is 0. So that first part of the function approaches 0. That's what that limit's equal to. This is equal to 0. What does that mean? Okay. If I'm going to dispense with the limit notation because I think you can be corralled into an incorrect conclusion about things not existing if we stick on limits. If 2x over x squared, 2x squared plus x minus 2 approaches 0 for large values of x, then 2x over 2x squared plus x minus 2 plus 1/3 x plus 3 approaches 1/3 x plus 3 for large values of x. Because this thing, and I know this gets repetitive, but I almost have to repeat it myself to make it clear in my head what's going on. It's tricky. This thing contains a big thing that approaches 0. And if that thing that is approaching 0, this whole term is approaching 0, then that whole function is approaching the thing that is not approaching 0. And what we're going to conclude is that the graph will be asymptotic not to a number, but to 1/3 x plus 3. Whatever 1/3 x plus 3 looks like, when you start to go to large values of x, the graph of the function we're talking about gets closer to that line. It doesn't get closer to this line because it's not a constant thing it's approaching. So we are asked to confirm our response using a graphing calculator and do a rough sketch. So the first thing, I guess, is we should set up our window settings on the graphing calculator to match what we're looking at here in our handout. And if you didn't have a graphing calculator and we're learning this in post-secondary, you might graph it on a computer, which I am going to do in a bit. -6 to 5. Oh, I think I did this to check it out earlier. So I'm going -6 to 5 and -2 to 7. And I'm going to enter, oh, I already have it in there. So I'm entering 2x over 2x squared plus x minus 2. And I've got that 2x squared plus x minus 2 in brackets. Then I have plus x over 3, and then I have my plus 3. And this is what the thing looks like. First of all, before we commit ourselves to drawing anything on paper, and by the way, we could do a full-blown first and second derivative analysis to find out inflection points and all that. I now know why I have a 2 under there. This factors into 2x and x and 2, no, doesn't factor, does it? But if you were to set that equal to 0, you would get 2 solutions for it being equal to 0. So you're going to have 2 asymptotes. We have time. Let's do that. Let's find out where those asymptotes are. So I'm taking 2x squared plus x minus 2. Is that correct, Annalie? Yes? Okay. Equal to 0. Thank you. So I'm going to have negative b, which is -1, plus or minus the square root of the discriminant over 2a, which is 4. I want to say 17. So at -1 plus the square root of 17 all over 4, there is a asymptote. And at -1 minus the square root of 17 all over 4, there is an asymptote. Let's just, for kicks, figure out what that is. The first one's going to be very close to 3/4. It's going to be 0.77 or 78 maybe. 0.78. And the other one is going to be very close to -1.25. I'm going to say -1.28. So looking at our graphing calculator, that's where those asymptotes are. Okay, you can see there's some asymptotic nature there. If we wanted to, we could put those in. I'm not going to hand out rulers. We can just do it roughly. I'll even just do it freehand. We've got an asymptote there. Whoa, at about at about 0.78. We have another one at -1.28. Was that right? Okay, -1.28. Doesn't have to be perfect. I now know why I don't have that 2 in mine. I think if I got rid of the 2 in my note package, it's factorable. So we have some curve in the middle. It looks like it's going through about 1.5. It's coming down here, but I really don't care. We have some curve that does that. And then we have 2 other curves. But before we sketch them, the claim was that y equals 1/3 x plus 3 is an asymptote. Let's graph on the same grid y is equal to 1/3 x, which is x over 3, plus 3. So that line that's just been drawn is not the function we're interested in. It's not a function at all. It's not part of the graph. What it is an asymptote of the graph. So if I were to draw in 1/3 x plus 3, and you should know what 1/3 x plus 3 looks like. You should know that it has a y-intercept of 3 and a slope of 1/3. So it should be fairly easy for you to construct that graph, that line. But when you draw it, and I'm not going to try to draw an angle freehand, it is an asymptote. Which means the graph of the function is asymptotic in this corner, and it's asymptotic in this corner. And that's the meaning of a slant asymptote. I don't think I would expect you in this class to sketch these graphs, but in the end, that's what it's going to look like. And when I said on your exam you will be expected to work with slant asymptotes, I would never give you a function on an exam and say graph it entirely if there's a slant asymptote. Okay? The only time you're interested in slant asymptotes is if I ask you on an exam, what's the equation of the slant asymptote? I want to show this to you in a slightly different way. There's a nicer graph, better than I could ever draw. What I've got is an Excel spreadsheet, and the very last column is f of x. If you look at the top here, I've got the equation of the function for f of x. And then I've broken it up into 2 parts. So if you were to look at the equation I'm using for this cell, it's going to be the sum of these 2. Are you guys taught how to use spreadsheets? No, eh? I put in a formula here, and then what I do is I give the spreadsheet program, that's not what I wanted to do. Then I give the spreadsheet program a set of instructions, and that set of instructions is to take and copy this down, but it changes for every row. It duplicates the rule, it repeats the rule. So now what we look at here is the fact that when x is 1, 2 is the first part of the function, 3.3 is the second part, it adds to give 5.3. If I take a look at the proximity between 1/3 x plus 3 and the whole function at x equals 1, they're not close. But as I scroll down, what happens is those 2 columns get closer and closer together because the first column is approaching 0. That first column is the part of the function that is approaching 0. And if you scroll down enough, I don't know how many rows I created, but if you scroll down enough, well, I'm not going to stand here like an idiot all day doing this, but I think the point is made that the function, which is the last column, is approaching the second to last column, which is only 1/3 x plus 3, numerically. So the y coordinates get very close to that line. Any questions before we get to the examples now? All right. What's the slant asymptote of this function? Let me write out the function. It's y equals 2 over x squared minus 3. and then I have minus 4x plus 2. Well, the slant asymptote will be y equals negative 4x plus 2. Because this approaches 0 as x approaches infinity. And again, I don't want to spend class time today doing limits. How many of you see that this thing that I've got the green cloud around will approach 0? The limit as x approaches infinity of this is 0 because the degree on the top is smaller. Okay. That's it. That's all we have to do here. Now, that's not the entire lesson. There's more to it. But let me show you what this looks like, because some of these graphs are interesting. If I were to graph the original function, and I have to graph it in pieces to show you it effectively. That's it. That's the function. And I could put in here as well, I don't want that. I could put in, yeah, I do, the asymptotes. There's a couple of vertical asymptotes. But you can see here that this arm on the right-hand side to the left of, say, the number 2 on the axis, on the x-axis, it continues to go down. It's not kind of leveling off towards some number. It continues to go down. And if I were to graph negative 4x plus 2, it looks like that. So in this middle region, in this general region here, the graph does not look like that dotted line. But as I zoom out, I better turn the whole function on. There's the whole function. As I zoom out, I'm going to push it to the limit here. As I zoom out, the graph of the function is really turning into that line. I mean, if you were to look in this region, I think you would say it's indistinguishable from that line. But it's only if you were to zoom in, you would see it's not the same. Any questions or comments on that first example? Right? Now, next page. If a rational function is written as a single rational expression, let me go back and show something to you. That this, in example 1, is set up so that we can see g of x and h of x. Right? There's two separate pieces to this. There's the 2 over x squared minus 3 and the negative 4x plus 2. In the other warm-up, we had the same thing. We had it separated out. So now this is saying, what if it's like that? What if somebody has put them all together with a common denominator? And I'm telling you that any time the degree on the top is 1 more than the degree on the bottom, there will be a slant asymptote. Okay? I can show this to you. Happens to be a vertical asymptote. This is the slant asymptote. There's one there. But now the problem is, how do we find it? So what is the equation of the slant asymptote for that function? We have to do division. We have to divide that polynomial of negative x squared plus x plus 1. We need to divide it by x minus 1. And remember that that original function is equal to the quotient plus the remainder over the divisor. Does that ring a bell? More so to those in Math 30-1 right now. Let's do the division first. I can do synthetic division here, negative 1x squared plus 1, because it's plus 1x plus 1. I don't know, and we put the 0 of the binomial here. Does somebody remember, maybe, why can we do synthetic division here? Why are we allowed to? Because you're not always allowed to. Will?
You're dividing by a fact or a term of x minus something.
Right, it's the binomial we're dividing by is a binomial that's linear, and the coefficient of the x is 1. It's x minus a, or x plus 3, or whatever the numbers are. If I look at the next example, we're not going to be able to do that. Okay. So what are we going to get? Let me clean this up just a little bit. I bring the negative 1 down. I multiply the 1 by the negative 1 and get negative 1. Interesting. I add these and get 0. I multiply 1 by 0 and get 0, and I add these and get 1. What does this mean? It means that negative x squared plus x plus 1 over x minus 1 is equal to the quotient, which is negative x. If we divide into a quadratic, we get a linear in synthetic division. So that negative 1 here represents an x plus the remainder over the divisor. But this thing right here, this is f of x. So f of x is equal to 1 over x minus 1 minus x. And I've just written it that way, everybody, because we typically have this part which approaches 0, written first. That's just the way it's presented. It's g of x plus h of x, where g of x approaches 0. And that means this is our slant asymptote. Of y equals negative x. And if you're rule-oriented, and I know some of you are, if you're a rule-oriented, when the degree on the top of your rational function is 1 more than the bottom, your equation of your slant asymptote will be the quotient of the division. Because the remainder divided by the divisor will always be lower degree on the top than the bottom, so it will approach 0 at infinity. We can take a quick look at this. I mean, I already showed it to you. Here's the function. Here's the function in its entirety, just extended out, but I just like to have the arrows on there. There does happen to be a vertical asymptote at 1. This, I don't know if you can read that, but it says f of x equals negative x. That's the slant asymptote, and it matches, it lines up. Any questions with that example? Go ahead, Will.
Can there be a slant asymptote and it be the only asymptote of a function?
Yes. In other words, can this happen if there are no vertical asymptotes? And I'm going to say yes because, and I had to think about it just briefly. I'm going to say yes because the only reason something like, I want to go to this. The only reason this has 2 asymptotes, by the way, this would be vertical asymptotes at plus or minus root 3. Do you see that? The only reason that has vertical asymptotes is there are zeros of the denominator. Would you, and you understand why negative 4x plus 2 is the slant asymptote? Okay. If I do this, I can't have any vertical asymptotes, but I still have to have a slant asymptote. And that's an interesting question. Let's graph that, which is not, I mean, I want to make sure you understand what we're talking about is not that graph. It's something different. So I'm going to go ahead and graph it, and I'll be upfront with you here as well, that going through the whole gamut of first derivative, second derivative, symmetry, and all that, when there are slant asymptotes is a real pain. So we're not going to go there. Let's see. All right, what do we got? We have 2 over bracket x squared plus 3 minus 4x plus 2. I'm going to, for kicks here, put negative 4x plus 2 as well. And I'm going to make it a little dotted line. Okay. So 2 over x squared plus 3. In other words, I've set this up so the domain of this function is any real number because there are no non-permissible values. I want to be careful because it could be, maybe, that if you were to put these together with a common denominator, it could be that you do get a non-permissible value in the denominator. Out of fluke, right? I'm hoping we don't here. But I hope even if we do, you can conceive of a situation where we wouldn't. This is a really interesting one. I'm going to go zoom standard first. And it's approaching it very quickly. I think if I change this to 6 over that, you can see it's not approaching it as much, so you can see the approach there. I'm actually going to really, let's go 6, insert, let's go 66. And I'd be willing to bet that if we look way up in the left, I have to go up quite high. I don't know, 1200, it might be too much. Negative. I'm just estimating here. Oh, well, went way too high. I've zoomed out enough that I hope you can appreciate that dotted line is being covered up by the solid line. So it is asymptotic in both sides. I do have a different one to show you here that maybe it will, there we go. Well, it's this one. It's the next example. Okay? Let's look at the graph of the next example first. In answer to your question, this written as an entire rational expression has 0 non-permissible values. When I look at this graph, that's what this is what it looks like. And the dotted line is the asymptote that we're going to find. If I were to zoom out more, go further out, it looks like that. If I were to zoom out even more, it looks like that. And far out, it looks like that. So at some point, if you zoomed out enough, you wouldn't be able to see that there's a separation between the two. Have I answered your question? Okay. So the degree in the numerator is 1 more than the degree in the denominator. The rule I've given you is that there must be a slant asymptote. The reason is when you divide a degree 3 polynomial by a degree 2, you get a quotient that's a degree 1. And the quotient is going to be the part that's not approaching 0, because the other part will be a rational expression that does. So how do we do this? We can't use synthetic division. We have to take x squared plus 1 and divide it into 2x cubed minus 3x squared plus x minus 3. And I think you probably will remember when I taught you Math 30-1 that we did long division, and you could just see some of the heads kind of swelling and getting close to exploding because it's complicated and it's easy to make mistakes. But I told people, don't worry too much about it. The only reason I'm doing this is so if you take calculus, you've seen it before. All right? So what we want to do is when we do the division, I'll back up. When you do division, long division, there's a series of stages for each layer. You divide, you multiply, you subtract. Then you repeat. When you divide, you only worry about dividing the highest degree terms. So what I'm saying in my head right now is what happens when I take 2x cubed divided by x squared? And the answer is I get 2x. So the quotient of that is 2x, and I write it above because it's part of a quotient, but I put it in the column that has the x's. Now I multiply, but when I multiply the quotient by the whole thing. I ignore that 1 to begin with, but now I multiply. So I go 2x times x squared, which is 2x cubed, and then I have 2x times 1, which is 2x, and I put it in the column that things are lined up with. And then I subtract. So this is the third step in the first layer of this process. So I have to subtract that. 2x cubed minus 2x cubed is nothing, so I don't have to write anything. Now, what do you do here? Negative 3x squared minus, well, some people might want to put that there. Just to make sense of it. I do. Unless I see that there, I'm a little confused as to what it is I'm supposed to do. So negative 3x squared minus nothing is still negative 3x squared. And then x minus 2x is negative x. And you bring down the next item. You don't have to bring it down right now. We're about to do something again where at some point you're going to go, wait a minute, I need that number. Double checking 2x times x is 2x squared, 2x times 1 is 2x. And when I subtract, I get negative 3x squared minus x, and then I have that minus 3. Now you repeat. The only thing that's different here is now you're doing that division. You are now taking 3x squared, negative 3x squared rather, divided by the x squared, giving negative 3, which we put up top. You know, at this point in time, if you're really on top of things and following me, you have the equation of the asymptote. It's 2x minus 3. I'll come back to that statement in a minute. But we have to multiply that 3 now, that negative 3 rather, by the x squared plus 1. Negative 3 times x squared is negative 3x squared. Negative 3 times 1 is negative 3. We subtract, and you're going to get negative x. The negative 3x squared minus the negative 3x squared is a wash. The negative 3 minus the negative 3 is a wash as well. So why is it that I know this is the slant asymptote? How do I know that? Because the division algorithm says that that original function, and I'm going to actually write it out, it's 2x cubed minus 3x squared plus x minus 3 over x squared plus 1. That original function is equal to the quotient, which is 2x minus 3, plus the remainder over the divisor. And since we started off with a higher degree by 1 on the top, it is a guarantee, a 100% assurance that this thing, your remainder over the divisor, will have a lower degree on the top. If it didn't, then we didn't do the division right, because you could keep dividing. Your remainder has to be a lower degree than your dividend. And this thing that I've circled is what will approach 0. This is not something that I think you would have to show work for. It would be a multiple choice kind of thing. If you were expected to do this on a written response, you would then have to say, well, the limit of this thing I've circled as x approaches infinity is 0, so the whole function approaches 2x minus 3. Just to show this to you, going back to the graph, I'm going to go to an intermediate one, this one. There it is. I don't know if you can see, but on the left-hand side of the screen it says f of x equals 2x minus 3. That's the dotted line, which is the asymptote. Any questions with that example? Or any questions? At some point, you need to maybe familiarize yourself with the idea that if the degree on the top is 1 more, then when you do that division, the quotient will be linear. But at some point in your math career, you may encounter nonlinear asymptotes. If you were to do division here, you're going to get x squared plus 1 over x. And 1 over x produces 0 at infinity. So let's look at the graph of this. That's the graph of y equals 1 over x plus x squared. 1 over x approaches 0 as x approaches infinity, so y will approach x squared. Can you kind of see a parabola there? I mean, not in the center, but as the graph goes away from the center, there's a parabola. It doesn't matter what the graph looks like in between. What matters is what the graph looks like as you go to larger values of x in either direction. Y equals sine x plus 2x over 3x cubed minus 1. I hope everybody understands that at infinity that approaches 0. So what we're going to have here is a periodic asymptote. We're going to have an asymptote that this original function will get closer to, and the function it's getting closer to is sine of x. So again, I've plotted this. That's it. That's the function. That's sine of x plus x over x cubed minus 1. 3x cubed minus 1. Or 2x over. It doesn't matter. Pretty wild looking thing. But if I were to graph the whole thing further out, that's what it looks like. And if I were to graph y equals sine of x, by the way, there's an asymptote here. Cube root of 1, which is, no, cube root of 1/3, I guess. There's the asymptote. That's pretty cool. If I zoom out, notice that at each time the outer part of the brown graph, which is the function, goes up and down a little bit, it's returning closer to sine of x. So it's approaching sine of x. And the more I zoom out, the closer it gets. In fact, to the point where I think if you look at the left and right part of the screen, it's hard to see that they're different. If I zoom out enough, this mess in the middle becomes kind of something that you don't even really care about. It's part of the graph, but way out here, in this region and in this region, it's basically sine of x, but not quite. Any comments or questions on anything we've covered today? You can make up any graph you want that's going to do this. Make any asymptotic function, make any function part of the original function and add it to something that's approaching 0. Y equals 1 over x plus that will approach this thing, because 1 over x will approach 0. I don't know what that looks like, by the way, and I don't care. All right, some practice stuff in your handout, or in your textbook rather, page 244, questions 1 to 3.